I'm Alona Fyshe. I'm a professor at the University of Alberta, and I'm also a fellow of the Alberta Machine Intelligence Institute. And I'm going to follow in Jessica's footsteps in that I'm not going to talk about exploration of the outwards, but rather exploration of the inwards and how we know what we know and how we could tell if a computer knew something too. So you probably interacted with Siri or somebody like Siri, either on your phone or maybe you have an Amazon Alexa in your house. I have had the experience of saying, hey, Siri, call my mom. And she does actually place a call to my mother. But do you think that Siri understands the concept of mother? Do you think she understands the concept of call, even though she's a phone? I think she doesn't understand what even call means. And so I'm interested in asking, how do computers understand meaning and language? And how could we tell if they understood what we said? So how do we test understanding? So if I was trying to test whether a person understood what I was saying, I would ask them to do something, and if they did the right thing, then I could say, oh, they understand me. But we've already decided that that's not how we want to test Siri. Siri does what we ask her to do, but we still don't believe that she understands us. So let's think about how we test students. We test students every day, and we do things, ask them about things in their world, things that we've taught them to see if they know what they've learned. And so one thing that we can do to test students about what words mean is to do analogy tests. So hammer is to nail as screwdriver is to screw. Very good. Excellent work. Hammer is to nail as screwdriver is to screw. You're right. So this tells us that you understand the individual words and also the relationships between the words. And so do you think we could get a computer to do this task? And so that's the first thing I'm going to talk about today. So we're going to use, in order to solve analogies, we're going to use computer models of word meaning. So computer models of word meaning are built on the fact that words that are similar are used in similar ways. So if we were to look through all of the websites on the internet and look for the word car and the word truck, they would probably both be used in similar contexts. They would both be used with the words gas, drive, door, steer, etc. And so that would tell us that they have similar meaning. And so what computer models of word meaning do is to use that, leverage that fact in order to build models. So we're going to calculate statistics about the word co-occurrence when two words occur together, and we're going to turn those statistics into lists of numbers. When words have similar meaning, they will have similar lists. So here I'm representing the numbers with the color blue, and if it's more blue, then it's a larger number. And so these two words, car and truck, I've made a short list here, and because car and truck are similar, they have similar lists of numbers, but they're not exactly the same. So we can use this idea of lists of numbers in order to tell if two words are similar. So hammer is to nail, as screwdriver is to screw. Now we need to use these lists of numbers to actually perform the analogy task. So what we're actually going to do is literally do math on these lists of numbers. So we're going to take the list for nail and subtract the list for hammer and add the list for screwdriver, just element by element. And that gives us a new vector. And it turns out that, new list of numbers. And that new list of numbers tends to be close to the correct answer to analogy tasks. So this hypothetical list of numbers is close to the co-occurrence statistics we see for the word screw. So let's test our computer model. We're going to do the analogy test where we choose from 5 options. And so if we were randomly guessing, if you didn't know what you were doing, you would get 20% on this particular test. So the average US college applicant gets 57%, so better than guessing. And it turns out these word lists that I just told you about actually do almost as well as the US college applicants, so 56%. So do computers understand language? Are you convinced? So I think it would be right for you to still be skeptical. I am also still skeptical. So I think we both can agree that computers do not understand the meaning of words, even though we've performed these analogy tests as well as US high school students. So let's go right to the source. Half of my work is also on brain imaging and studying what language looks like in the brain. So let's see what word meaning looks like in the brain. So the way we're going to do this, remember our computer models are just lists of numbers. Turns out that brain images are also just lists of numbers. So for a particular area, the list of numbers represents how much activity there is in that area. So in both cases, we just have lists of numbers, and we can tell how similar the lists of numbers are, and we can use that in order to compare the two sources of information. So essentially what we're going to do is take pairs of concepts, so things like dog and cat, car and truck, and we're going to compare how similar they are in using the list of numbers from brains and using the list of numbers from computer models. And so we would like to rank these lists of pairs and check if the ranking is similar across their two data sources. And if it's similar, then we would say that computers understand things in the same way that the brain does. So this is your brain. On the top is the left side of your brain, and the bottom is right. And I'm highlighting here just the areas of the brain that are known to be involved in language processing. So I just want you to remember that there's a few little spots here, and most of them are on the left-hand side. And so now on the next slide, I'm going to show you essentially the results from comparing a computer model of meaning to a human brain. And so here we're going to be coloring the brain with these colors that represent how correlated those rankings are. So if it's red or yellow, it's very correlated, and if it's more of a blue, then it's less correlated. And if it's gray, then it's not significant. There's no significant relationship between the computer model and the brain. So here, the first thing to notice is there's nothing that's gray, which is remarkable and interesting and not something that was known before this research was started. We thought language was really relegated to these one pieces, but it turns out that language meaning is all over your brain. You understand language with your entire brain. We also see the same pattern of some more red and yellow on the left-hand side, but we see language meaning all over the brain. And this shows up in other studies too. So this is brain images captured while people listen to podcasts. And so here, if anything is black, that means it's also not significantly related to the computer model of meaning. But here we see lots of parts of the brain are not black. And that shows us that this computer model of meaning is related to how your brain registers meaning as you're listening to a podcast. So parts of our brains do represent meaning in the same way that computers do. So computers think like us. Are you convinced? I think you're right to remain skeptical, but it's interesting to think about what it would take to convince you that a computer understood language. Good. Thank you very much.